So welcome back to our Post-Brexit Finance and Coronavirus Challenges Conference. I'd like you to join me in welcoming our next keynote speaker today. Ladies and gentlemen, Oswald Distinguished Professor William Barnett is Director of the Advances in Monetary and Financial Measurement at the Center for Financial Stability, the CFS in New York, and Director of the Institute of Nonlinear Dynamical Inference in Moscow. His current work is in the fields of chaos, bifurcation, and nonlinear dynamics in socioeconomic contexts, econometric modeling of consumption and production, and the study of the aggregation problem and the challenges of measurement in economics, especially in financial and monetary economics. His MIT Press book, Getting It Wrong, won the American Publishers Award for Professional and Scholarly Excellence, and his book with Nobel Laureate Paul Samuelson, Inside the Economist's Mind, has been translated into 6 languages. He is founder and was the first president of the Society for Economic Measurement, founding editor of the Cambridge University Press Journal, Macroeconomic Dynamics, and of the Emerald Group publishing monograph series, International Symposia in Economic Theory and Econometrics. Oswald Distinguished Professor William Barnett is the originator of the Divisia monetary aggregates and the Barnett critique. He is a fellow of the American Statistical Association, a charter fellow of the Journal of Econometrics, a charter fellow of the Society for Economic Measurement and the fellow of the World Innovation Foundation, a fellow of the TANDO International Policy Institute, and a fellow of the Johns Hopkins Institute for Applied Economics, Global Health, and the Study of Business Enterprise, and Honorary Professor at Henan University in Kaifeng, China. Special issues of the Journal of Econometrics, Econometric Reviews, and the Journal of Financial Stability have been published in his honor, and he is ranked among the top 2% of the world's economists in RePEc. So the title of this keynote presentation today is the Brexit bifurcation causing chaos in the United Kingdom? So without further ado, I'd like to hand you over to William Barnett. Thank you, Bill.
Well, thank you, Jane. I would like to thank you for organizing this very productive conference and inviting me to be a keynote speaker. I hope one day I will get to return the favor by introducing you as a keynote speaker at another conference.
Thank you, yes.
I should mention in advance, I have a lot of slides. I have 64 slides that I'm going to go through. They do not include any math, so I'll be able to go through them relatively rapidly. The math is quite difficult. If any of you really want to see the math, just send me an email message and I will send you one of the 2 relevant papers. Let me now try to share the screen and get this going. I hope you can all see that now. Is that visible to everybody?
Yes, yes.
Okay. First, let me mention, I'm over here on the other side of the pond. I know very little about the politics of this, and I'm going to say absolutely nothing about the politics of this. I'm sure many of you know much more about that than I do. I'm going to look at this strictly as an economist. As an economist, this is a really fascinating opportunity. It produces a rare kind of a controlled experiment that is not often available to economists. But there's a complication, which is the pandemic. The pandemic, its economic effects are confounded with the effects of Brexit. So to fully research the consequences of Brexit, we're going to really need to wait until the pandemic is over. It'll probably be a couple of years before we'll be able to do a really careful comparison of pre-Brexit versus post-Brexit. So let's first look at the pandemic. The pandemic is dramatically different from Brexit, which makes it a very interesting comparison. What the pandemic does is it produces external stochastic shocks to the economy from the virus. But Brexit is very different. Brexit is something internal. It's some sort of intentional bifurcation. So that's what makes Brexit so interesting. The pandemic, again, we're mostly looking at the consequences of external stochastic shocks to the economy. But when we look at Brexit, we're looking at something internal to the system. So first, let's ask, is Brexit increasing economic risk within the UK? Well, I don't know the answer to that. Like I said, I'm on the other side of the pond. From what I've read, there are different views about this. Advocates of Brexit believe that it will decrease risk. But if you look at what Brexit is doing, basically, if you start out with a model of the EU and you impose Brexit on a model of the EU, you're either adding or removing constraints to the system that link the UK to the rest of the EU. In some cases, some constraints are removed and others are added. But it's a kind of a bifurcation. It's a structural change imposed on the system if you start out by looking at it as the EU. Again, that's not the case with the pandemic. So now it's interesting to ask, does this bifurcation alter risk? Probably it does. I don't know how. There are different points of view. Maybe it increases risk. Maybe it decreases risk. I don't know. But everybody seems to think it changes risk within the UK. Now the question is, how and why would such a structural bifurcation alter risk when we're not talking about external stochastic shocks as from the virus? Now, again, I'm not talking about politics. Some people might want to say there are shocks from politics. I don't know anything about that. I'm just looking at this in terms of economics. So how would we explain this? How would we explain the possibility that Brexit is somehow altering risk, maybe increasing it, maybe decreasing it? How would we explain this as economists? Well, we could say there's been a change in subjective probabilities. People's beliefs have changed. Well, that's a very weak, almost circular explanation. That just says that risk has changed because risk has changed. That doesn't really help us at all. There's a more sophisticated explanation, which is sunspots. Now, sunspots are external shocks that are irrelevant to the economy, but affect the economy solely because people believe they will, sort of self-fulfilling prophecies. This is a very important subject in economic theory, but it's related to multiple correlated equilibria. So to be able to say that what's happening is that sunspot risk is increasing or decreasing, we somehow have to say that Brexit is altering the number of correlated equilibria, or altering irrelevant shocks that people believe are relevant. Well, maybe that's true. I'm sure there are economists who would want to argue that. If Roger Farmer were here, I'm sure he would want to argue that. But I don't find this convincing. I just don't see the linkage to Brexit. To me, it looks like a bifurcation. That's what an engineer would say. There's been an intentional bifurcation of the dynamics. Well, there are a couple of different ways that such a bifurcation could alter stochasticity. One is a bifurcation to or from chaos, because chaos produces its own kind of stochasticity from the fractal attractor set that induces a probability distribution. So it produces a deterministically based stochasticity. So if the bifurcation introduced or eliminated chaos, that could alter risk. But there's another possibility. Maybe the economy was already chaotic before Brexit and remains chaotic after Brexit. Well, that's another story. With chaos, there's an attractor set, so-called strange attractor, a fractal attractor set. The geometry of that attractor set is enormously informative. It's been shown it has all of the information in the real world. It's all embedded in that geometry. Hawkins proved this a long time ago. Brexit could have altered the geometry of the fractal attractor set in ways that would alter the stochasticity of the economy. Now, I'll tell you in advance, my original view when I started working on this with my co-authors was maybe it was number 3. Maybe Brexit was causing a bifurcation to or from chaos. But what I'm going to tell you is that research with my co-authors tells me number 4 is more likely. And I will get to that. This is the paper that my co-authors and I have completed using US data in a particular kind of chaos called Shilnikov chaos. What we've shown with US data is Shilnikov chaos does appear to exist in the US economy and has ever since an active Taylor feedback rule began to be used. So the source of this chaos is turning the economy into a servo mechanism. That's what the Taylor rule does. It turns the economy into a servo mechanism by the use of feedback, strong feedback from output to an input, which is an interest rate. And what we're finding is that alters the nature of the dynamics of the system and introduces Shilnikov chaos. Now, I want to say there's nothing wrong with chaos. In nature, practically everything's chaotic. So it's not intended to be a negative statement, but it's incredibly informative. Chaos produces informative stochasticity, not white noise, which is uninformative. So here's basically the conclusions of that research. I've already told you the source of the chaos. It's that feedback. That feedback, when the economy has new Keynesian sticky prices, we find produces Shilnikov chaos, which again is not necessarily something bad. But it has an effect, because remember, with chaos, everything is in the fractal attractor set's geometry. What we find from the fractal attractor set's geometry is downward drift in interest rates. So what we're finding is, since the Taylor rule became very active in the United States, in the UK and in much of the world, there has been a steady downward drift in interest rates. And this is an explanation of why. It's unintended. It just is the nature of the dynamics when there's Shelnikov chaos. Now, there are all kinds of other bifurcations as well. I will want to talk about other kinds of bifurcation as well. Bifurcations are normal with dynamical systems. Anyone who's familiar with systems theory knows it. It's very normal. Bifurcation can go from one kind of stability to another kind of stability, or from one kind of instability to another kind of instability. It does not necessarily go from instability to stability or vice versa. It's been found with many models of the US economy. My co-authors and I have found it with the UK economy, using the Bergstrom-Noman-Weimer Keynesian macroeconometric model of the UK economy, which I'll tell you about. Again, this is normal. Bifurcation isn't something that says there's something wrong. It's everyone who knows systems theory knows you should expect it. But now suppose we have chaos. Chaos is a very special kind of bifurcation. These are consequences of chaos, and I've mentioned the two most important. One is it produces a form of stochasticity that has deterministic origins by defining a probability distribution over the fractal attractor set, which is an unusual kind of geometric set. It's a Cantor set. It has those other properties too. But the one we really want to emphasize is the informative nature of the fractal attractive set, which is enormously valuable. Well, why do we care about chaos? Well, basically, I've just told you, it's because of the Dawkins theorem. It says we have informative stochasticity, enormously informative stochasticity. It can tell you everything if you can extract it all. There are examples. The weather is chaotic. Climate is chaotic. Human brain waves are chaotic. If your brain waves were not chaotic, you would be seriously mentally ill. Your brain would not be able to find its memories and you would be delusional. There's a fundamental difference between engineering and nature. Nature frequently produces chaos. Engineers try to devise systems that are not. It's a very fashionable area of research. Many of you have probably seen the movie Jurassic Park. You probably know the hero was a chaositician. There have been bestseller books on it, lots of articles in the popular media. It's a very fashionable topic. I even spoke once in the palace in Belgium with the king and queen there in the palace. Unfortunately, the king has subsequently died, but it was a fascinating experience. I mentioned systems theory. Engineers familiar with systems theory really depend upon bifurcation and chaos. They understand it's very common and you need to worry about it. Some of you probably know I started out as a rocket scientist. I worked for Rocketdyne on the rocket engines for Apollo. In particular, I worked on the F1 rocket engine. That's the booster engine that got it off the ground. It's still the most powerful single thrust chamber rocket engine ever developed anywhere in the world. Today, you might have heard about Jeff Bezos' Blue Origin launch, his tourist launch from West Texas. The rocket engine in that vehicle was based upon the technology of Rocketdyne's J2 engine, which was the second stage engine of Saturn, using liquid hydrogen and liquid oxygen. So how do you produce rocket engines? Well, you design it, you build it, then you put it on a test stand and you run it over and over and over again, thousands of times, to see when something goes wrong. And then you have to figure out, what do you do when something goes wrong? Well, what you find out is, when something goes wrong, the cause is usually something very small. We're talking about bifurcations that you want to fix, or it could even be chaos. But with the F1 rocket engine, when there was a bifurcation from maybe something very small, it blew up. And then we were up all night long trying to figure it out. That's the F1 rocket engine that I worked on. There is the F1 rocket engine being tested at Edwards Air Force Base. I can't even explain what it was like seeing and experiencing that. It's beyond description. That's the 5 of them that got Saturn V off the ground. You used 5 of them at the base of the vehicle, each producing 1.5 million pounds of thrust. There they are again. There is the Saturn vehicle. In short, I've known about bifurcation and have taken it very seriously for a very, very long time. Now, after I was a rocket scientist, I was at the Federal Reserve Board in Washington, D.C. for 8 years. And after that, I was a professor at the University of Texas at Austin. One of the professors there was Ilya Prigogine, a Viscount from Belgium. He won the Nobel Prize. He wrote a very famous book, Order Out of Chaos. It contains that statement that I don't completely understand. This further increased my interest in chaos. Well, he won the Nobel Prize for his work on chaos. So we had something in common. So I did some work with one of Ilya Prigogine's students, Ping Chen, a physicist. He got his PhD in physics with Prigogine as his dissertation advisor along with me. We ran the tests that physicists run to see if we could find chaos in economic data, and we did, and we published it. This might be the first finding of chaos in economic data. So we published it. Another question is this really important? Well, there are problems. To use those kinds of tests that physicists use, and to really be able to map out the fractal attractor, you have to have a huge sample. Well, physicists can run thousands of replications in a controlled experiment, but we can't do that. Another thing is, when these tests find chaos in economic data, they can't tell you where the source of it is. It could have come from outside of the economy, maybe from the weather. So you shouldn't really be surprised to find chaos in the data. It might not even have come from the economy. It might have come from the weather. So this is a very weak conclusion, and unfortunately not very informative, because we don't have large enough sample sizes to use these physics algorithms to produce the fractal attractor set. And that's the name of the game. What we want is that geometry. The next step is people wanted to maybe look at an economic model and see from an economic model whether or not they could detect chaos within an economic model. Then they could say it comes from the economy. Well, there's a really classic, famous paper by Jean-Michel Grammont in Econometrics. It's a brilliant model, everybody knows it. There's also a very important paper by Baduri and Harris that also found chaos in the economy. What most of you probably don't know is who's Donald Harris. Donald Harris is Kamala Harris's father. Kamala Harris is currently the Vice President of the United States. So those are very important papers. But in all of them, the solutions are Pareto optimal. They're not Keynesian models. There are no forms of market imperfections or sticky prices. So the problem is, yeah, there's chaos, but why do anything about it? If it's Pareto optimal, if you try to intervene to control or stop the chaos, you might be producing a harm. So you don't want to do it. Well, then I worked with one of my co-authors, Ijun He, on the UK continuous time macroeconometric model. And this model is Keynesian, and it is of the UK economy. So this one's policy relevant. We published papers on these results in a few different places. This is the model we used, mostly associated with the Bergstrom, but also Weimer and Neumann. You can look up those sources if you're not familiar with them all. It's a very interesting, and it's a continuous time system of differential equations. It's a very good model to be looking at in terms of dynamics. This is the structure of the model. You could look it up if it interests you. Here's an example of a kind of bifurcation, very famous, well-known to economists, called Hopf bifurcation. In this example, when theta equals 0, it bifurcates. So if theta is negative, what happens is you get damped cycles that end up at the steady state. So it's stable. It oscillates and damps. If you're a little bit to the right, you get positive theta. It's never going to damp. It's going to go into cycles and it's going to stay there. The farther away you get, the bigger the cycles. Anyway, this is a very famous kind of bifurcation. So here's the Bergstrom model. We want to plot it so you can see this. So we produced three-dimensional sections through the space. So the full space has higher dimensions, but we can only plot it with 3 dimensions. So we had to hold some parameters constant and just vary 3 of them. And we look at the confidence region and the theoretical feasible region. I should perhaps mention, we did not estimate the model. We used Bergstrom's estimates. So don't blame us for this. This is Bergstrom's work, his confidence region, his point estimates. The stable region is inside this complicated looking set. If you look at this 3 dimension, it's 3 parameters. These are 3 parameters that Bergstrom said were very important. Looking at it relative to these 2 different sets, the confidence region and the theoretically feasible set, which is a bigger set. This is a different 3-dimensional section. Notice we labeled the kinds of bifurcation as Hopf, also transcritical bifurcation. The point estimates are slightly outside the stable region. So the Bergstrom conclusion was the UK economy is slightly unstable, and in one of his publications, he advocated a fiscal policy feedback rule to stabilize the economy. Now, there's a possible problem with that model. The authors of the model deny it, but some people believe it might be vulnerable to the Lucas critique. So we decided to do this again with a model that's definitely not vulnerable to the Lucas critique. That's the Leeper and Sims Euler equations model. This is deep parameters. This was designed to have deep parameters. we found singularity bifurcation, which is a worse kind of bifurcation. So this doesn't make it better, this makes it worse. It changes the order of the dynamics. So this is a very severe kind of bifurcation. Now we wanted to ask, what about a real simple little model, a model everybody would know about? In fact, a linear one. So with one of my co-authors, Evgenia Duzhak, who's now at Berkeley and the San Francisco Fed, we used the simplest linear 3-equation new Keynesian model. It has 3 economic agents: household, firm, central banks, linearized around zero inflation steady state. That's 3 equations: a Phillips curve, an IS curve, and monetary policy rule, all 3 linear. Monetary policy rules going to be a Taylor rule, or a special case of the Taylor rule, which would be an inflation targeting, which is really a special case of the Taylor rule. Here are our conclusions. It bifurcates. Notice, under almost every circumstance that we could consider for various kinds of rules, it's got bifurcation problems. And it's a linear, no less. Again, system theorists will say, well, of course, this is dynamics, that's what dynamics does. Well, subsequently, we published more papers on this using other models, increasingly sophisticated. Here's some of the most recent models. One of them was Unal Erelmaz using an open economy model. And another model looks at generalized Taylor rule. It always does the same thing. Whenever you do this, you're going to find the bifurcation boundary. It's normal. But now what about bifurcation to chaos? This is a particularly interesting kind of bifurcation. It's got all kinds of problems. First of all, if you want to test the hypothesis, you have to find a subset of the parameter space that supports chaos. How are you going to solve for that set? It can only be done analytically with 3 parameters. Well, no useful macroeconometric model has only 3 parameters, so we can't find it analytically. It could be done numerically. Very few people try it, but it's doable. Suppose you could find that set and you wanted to test the hypothesis. It would be very hard. Because when you go across that set, the set that supports chaos, you're on a fractal. That causes the likelihood function that singularity is all over it. This violates the regularity conditions for all kinds of statistical inference available to statisticians. So we don't know how to test the hypothesis. But we're back again. We have good reason to want to do this. It's got all the information in that set. Next step would be calibrate a model. Well, that's another story altogether. One could calibrate a model and check whether or not there's chaos at the calibrated settings. This is what a lot of macroeconomists do now. Jess Ben Habib and his co-authors have done this a few times. They have found with new Keynesian models, if you calibrate them, they find chaos. But they didn't produce the fractal attractor set. So just having general chaos again, we don't quite know what to do with it. Well, there's a solution. The solution is now very popular among physical scientists. What they've found is there are special cases of chaos that are widely relevant. So instead of just testing for general chaos, what physical scientists are now doing is testing for special cases that they know are widely relevant. Here are examples. You can see there's loads of them. We're using Shilnikov chaos for the reasons on that slide. There's a direct way to check for it, and it has been found to be amazingly widely relevant to natural phenomena. Here's an example of how widely relevant it is. This is well known to physical scientists. Unfortunately, very few economists have ever even heard of it. Incidentally, while Shilnikov died many years ago, he was a very famous Russian mathematician. His son is alive, and he's in the United States. He's at the Georgia State University in Atlanta. He has an endowed chair in the mathematics faculty. If you want to work in this area one day and wish to correspond with him, he's very encouraging. He was, in fact, a student of his father's. So this is what we've done. We've decided to look at a new Keynesian model this is with the United States, and to check for Shilnikov chaos at plausible settings of parameters. We found it. We found it was associated with Taylor rule and sticky prices. If there's no Taylor, if there's no interest rate feedback, you don't get it. Now there's this interesting result because we've got Shilnikov chaos. Once we have Shilnikov chaos, we know how to get the geometry of the fraction. So we did. What it told us is interest rates will drift downward unintentionally. So it says that central banks didn't do it intentionally. They were not pulling a trick on us to try to decrease Treasury debt service, which some people think is some sort of conspiracy. It wasn't intentional. It's just the nature of what happens to the dynamics of the system when you have this kind of feedback. It's also an alternative explanation for why we are now in something that people would call a liquidity trap. The most common explanation for this is the so-called loanable funds theory, which says it was caused by over-saving by consumers. Well, you might believe this. Has been a lot of published research supporting that. I find it very paradoxical. People often ask, why has the United States been running a trade deficit with China? The usual explanation is the exact opposite. Too much consumption, not enough savings in the United States. So how can it be over-saving that's causing the declining interest rates when it seems to be under-saving that's causing our trade problem? Again, I would say it's a completely unintentional drift. Now we decided to do it with UK data because of this conference. So my co-authors and I repeated the analysis using UK data. We needed a model. So we looked around, we wanted a model. We didn't want to be our model, we want a widely respected model within the UK. We found this one, which seems to be well known and widely respected within the UK. There's a working paper version, Bank of England. It's also published in the JMCB. We decided to use this model. The data is from 1970 to 2009. We used their data. We didn't do this. We used their data, their parameter estimates, etc. Down here, you can see there are various cases produced by their model. There was one particularly interesting case. If you look at what's down there in red, you'll see the same thing that we found with US data. We find Shilnikov chaos associated with the strength of the interest rate feedback. This is what's been happening to the UK economy. It has to do with interest rate feedback. There's been strong interest rate feedback since 1992. With that particular model, there are two regimes that we found to be particularly revealing. One of them does not produce Shilnikov chaos. The other one does. The one that does is the one with strong interest rate feedback. That's what does it. This is just describing the two. There's the one without Shilnikov chaos. This is the one with it. The difference is interest rate feedback. Basically saying the same thing again. It's all about the interest rate feedback. If you don't analyze it in this way and you just look at it in terms of local analysis, you do not detect this. That's what this says. The usual local analysis won't find it. But with Shilnikov chaos, finds it. Now here is the ultimate conclusion. We really would need a few more years of data post-pandemic to see what's happened to the fractal attractor set because of Brexit. My view is this is a potential gold mine of research for economists. Once those data become available, we can do this. We can't do it yet. This is again saying what I just said. But again, the confounding with the pandemic prevents us from doing this comparison with current data. But with future data, we can do it. The Shilnikov criterion produces a very straightforward result. In fact, the results that we had prior to the pandemic using UK data with Shilnikov chaos, we're going to submit it to one of the proceedings volumes of this conference. And that's one other thing I just wanted to mention. If this subject interests you, you might want to look at that research center in Moscow that specializes in nonlinear dynamical inference. I'm the director of that research institute, and people with this kind of expertise from many fields all over the world are fellows of this institute, physicists, mathematicians, some economists. It's a good place to look. And I think I'm supposed to stop now, so let me stop. Okay.
So without further ado, could we open up now, please, for any questions? We'll do the formal thanks in a moment. If you've got any questions, please, could you type them into the Q&A or raise your hand, or you can speak directly if you unmute yourself. Thank you.
Well, if nobody's going to ask a question, I'm going to ask a question of myself. So a good question would be, if there is Shilnikov chaos in the US economies and the UK economies, what should the central bank do about it? Again, chaos isn't necessarily a bad thing, but liquidity trap is kind of a problem. It undermines the usefulness of the Taylor rule. Well, we looked into this. Engineers and scientists who are experts in this area have produced algorithms on how to control chaos. This would be a relevant way to retain the Taylor rule feedback while controlling the resulting chaos. What we found is, to do this, it's necessary to have a second instrument of policy, not just a short-term interest rate. There needs to be a second instrument of policy, which in some sense would be imposing a terminal condition, preventing long-term interest rates from drifting down to zero. And in fact, central banks right now are using other instruments of policy because they practically lost the usefulness of the short-term interest rate. But if they had started using a second instrument of policy along with the short-term interest rate a few years ago, when interest rates were higher, they'd still be higher and the Taylor rule would still be working. So a good way to do this is to institute a second instrument of policy when interest rates are above zero, to keep them above zero. Then the short-term interest rate can be used for short-term counter-cyclical policy while preventing the long-term interest rate from declining below the marginal product of capital, which is not really credible. Where it is right now is very hard to believe. Very few people believe the marginal product of capital is zero. Nobody who works for a corporation would believe that. There are other ways to do it also. One could use a different instrument of policy. One could use a monetary aggregate, a taxation instrument. There are many ways to deal with this. But the most interesting one is second instrument of policy.
Bill, we have a question from the floor, if we may.
Sure.
We have a question from Chris Courtwright about how long do you think we need post-pandemic data to see what happened to the fractal attractor set because of Brexit?
That's a very good question. Remember, what causes this approach to be so valuable is it can be applied with very small sample sizes. Economists were very discouraged about using chaos when the previous approaches all said you need huge sample sizes that we typically don't have. But with Shilnikov chaos, there's a very straightforward way to run that test. Sorry, my telephone's ringing here. You might be able to hear that. But anyway, a year or two of data should be adequate to test for Shilnikov chaos and determine the geometry of the fractal attractor set. But we can't do it now because of the confounding with the pandemic, which is hopefully going to be over. The sooner the better. But we don't need large sample sizes to do this by this methodology, which is now widely used by physical scientists. This is basically what they do. They have a half a dozen special cases of chaos and they check for them. And they almost always find one. If it's about nature rather than engineering, nature typically fits one of them, with Shilnikov being the most broadly relevant. So we do have this ability now to check for chaos and determine the geometry of the fractal attractor set with a small sample. This was not previously available. That's why economists became so discouraged. But now, because of the work of physical scientists and mathematicians, we now have the tools that permit us to do that with sample sizes that are relevant to economics.
And we have time for just one final question. We have 1 minute remaining now. So this is a question from Home Park. I think the chaos is a representative nonlinear system. Can we linearize the system? And if so, is it then meaningful? And this is the final question. Thank you.
The answer to that question is no. Chaos is impossible with a linear system. This is not widely understood. Many people think if you linearize a nonlinear dynamical system, you have a local approximation. That's true with statics. Unfortunately, it is not necessarily true with dynamics. If the truth is chaos and you linearize, you lose the chaos. So it is not a local linear approximation anymore. The only way to find and use chaos is with nonlinear dynamics, and you cannot linearize it. That wipes it out.
So thank you. That is the end of the Q&A session. So it remains for me to do the welcome, the thank yous for Bill Barnett's speech this afternoon. I should say that I first met Bill in 1986 in the Ironmongers Hall in London, and Bill was giving a keynote speech there 35 years ago. And I think now you can see why I'm still entranced and excited by Bill's teachings today. I'm lucky enough to have had the opportunity to prepare a book joint with Bill on functional structure and approximation and econometrics in 2004. So I've been lucky enough to actually experience working with Bill directly. I think you can see from Bill's credentials the extent of his work and how being a rocket scientist, a rocket engineer in Rocketdyne, working on the Apollo project, has really brought a new dimension to macroeconomics. So extending macroeconomics into bifurcation of Brexit and Shilnikov's chaos is really making this fully interdisciplinary and a fully inspirational field to work in. So thank you, Bill. I'd like the audience to join me to give you a big live thank you now.
Excuse me, but I would like to say something. Jane may not remember this, but I do believe I met Jane long before that. It was at a conference at the University of Mississippi that Mike Belanger ran. I believe I met Jane there a long time ago. I was impressed with her then, and I equally is impressed with her now. But we did meet a very, very long time ago.
Yes, that's right, in Mississippi, and there's still ongoing, excellent work ongoing there with Mike Belanger and Peter Ireland, so we're still very much all in touch. And this conference has given us an opportunity to connect properly remotely and to really exchange new ideas on Brexit. I'm really pleased that you think that Brexit risk is reduced using your analysis of bifurcation. I think that's provided a lot of comfort to people in the United Kingdom, and I hope that the data will show that as time moves on. So thank you very much, Bill. Thank you.